All right, good morning. This is our last new chapter of the year, and it's actually a pretty manageable chapter. We go back over a lot of concepts again from early on in the year. We do parametrics and vector valued functions. And I know that vectors were new when you were doing them in pre-calc. They're treated a lot like the vectors are in physics, and it's really a good unit to end with, a good manageable unit. So I'm going to go ahead and explain a little bit. I want you guys to send me that feedback like I talked about in my hello video. Make sure that you're sending me questions. They can be via email, via Schoology message, on ClassKick. Any way that you can get in touch with me. If you have questions and things that you want clarified, let me know. Okay, so x and y are both differentiable functions of t, and we know that dx dt is non-zero. Well, we know that dx dt is non-zero because we don't want to be dividing by 0. But when you find the slope of the tangent line, dy dx, you just take dy dt divided by dx dt. Imagine that if you multiplied by the reciprocal, you reduce the dt's. The second derivative with respect to x, I have to do a little bit more work because I'm not taking the derivative with respect to t. So it's the derivative of y prime with respect to t. So d dx of y prime is like taking derivative with respect to t of y prime. And then I have to divide that by dx dt. So that if I multiply by the reciprocal again, I would get the second derivative with respect to x both times. Arc length, we're going to go ahead and integrate. And what we're really thinking here is we're thinking Pythagorean theorem. So we're thinking a change in x squared plus a change in y squared is going to give you the change, right? A change in x, and this is a change in y. And then that's going to give you the length of a little line segment. So we're taking individual line segments and we're adding up all those individual line segments as we go to get the total arc length. All right, velocity, acceleration, and speed. Position is given by this vector, so then the velocity vector, just take the derivative of each component. Speed, though, is the magnitude of velocity. So then that is the length of the velocity vector, which is why we use, again, Pythagorean theorem. The acceleration vector is take the second derivative of each component for something like that. And then the arc length can also be thought of as the total distance traveled. Okay. So let's do one example together, and then I'll leave the rest for you guys to try and then take a look at the answers when you get a chance. The x-coordinate of the particle satisfies the equation dx dt for t greater than or equal to 3 with the initial condition x of 3 equals -1. Find x of t. Well, let's see. X of t would be some constant plus the integral of dx dt. Okay, so what I'm thinking is I would take this integral and I would probably do a u sub, but then the du is just dt. So it's a pretty easy u sub. It's just u to the -1/2. So then that's going to be what? U to the +1/2 divided by 1/2 or multiplied by 2 to get my x of t. Okay, use my initial condition, -1 equals 2 radical 3 plus 1 plus c. -1 is 2 radical 4 plus c. So -1 is going to be 4 plus c, and c equals -5. Okay, so x of t is going to be, what, -5 plus 2 radical t plus 1. Okay, I bet you guys can hear that in the background. One of my neighbors likes to race dirt bikes, and they're testing them out. All right, find dy dt in terms of t. Well, they didn't give me a dy dx. They gave me y equals x squared minus 2x. So dy dt is going to be 2x dx dt minus 2 dx dt. Think related rates here, right? So I'm thinking related rates. I'm thinking that I'm going to take all of this and I'm going to substitute it in for the value of x. And then I think I'm going to take what I know was my dx dt and sub in there as well. So dy dt is going to be 2 times negative 5 plus 2 radical t plus 1 times dx dt, which is 1 over radical t plus 1. And then, let's see here, I need to still subtract 2 times 1 over radical t plus 1. You can distribute that. You can simplify if you like. You don't have to simplify if you don't want to. All right, find the location and the speed of the particle at time t equals 8. Location and the speed of the particle. Well, I guess x of 8 should be reasonably easy, right? I have x of t. And they were nice enough to give us something where the square root comes out pretty nice. So x of 8 ends up equaling 1. If I want to find y, I can go ahead and use x squared minus 2x. So the location is going to be at the point 1, 1. But then let's see here, the speed, then I'm going to have to find what? Dy dt and dx dt, and then find the magnitude of those. I wonder if I might be better off using this part for dy dt. Let's see here. So dx dt is going to be 1/3. Dy dt is going to be 2 times 1 times 1/3 minus 2 times 1/3. Oh, that looks like 0, doesn't it? Well, so then my speed is going to be the square root of 1/3 squared plus 0 squared, or just 1/3.